So today I just want to finish up a bit of phenomenology before we talk about the specific mean field calculation of the Ising model. As I alluded to last time, most of what this class is about is phase transitions. And there's different ways of classifying phase transitions, but the way we want to do it in this class is simply first order or continuous. In U-O-U-S. Okay, there's other classifications. Okay, first order, this essentially tells you where the, singularity in the free energy, which derivative it occurs in. And you get a first order, second order, third order. But things like Clausius-Saulis transitions are infinite order, So I think a more modern way of looking at this is just first order or continuous. So first order is just characterized by discontinuity in the order parameter. So if you're doing an experiment on the magnetization of a ferromagnet, some nickel compound, like I mentioned last time, then you'll see a discontinuity in the thermodynamic limit. So, in the real system of 10 to the 23 particles, say. So the order parameter. So the thing that characterizes, the ordered pattern of the ground state, say for example, the magnetization is a function of temperature. At the phase transition, I'll call TC, but we should be a little bit careful with what C means. It usually means critical, and I'm reserving the word critical for second order transitions, but I'll just use it here to indicate the transition point. So a first order transition will have some sort of discontinuity in an order parameter. And for example, in say an energy, if you look at the energy as a function of temperature, well, it probably won't look like that. You could have some discontinuity, which would correspond to a release of latent heat. So that corresponds to the latent heat. You'll see big entropy gained or lost as you go through the transition. You'll see coexistence at first order transitions, because if you're sitting at or near the transition point, there's basically two, the probability distribution of say your energy has two peaks, right? That's one way of thinking about it. So like ice, ice to liquid water, it's a coexistence transition. You'll see hystereses. So if you, measure the energy in some sample and you cool it down, you'll see hystereses and things like energy or magnetization. You can see a hysteresis here and back up. Those are all signatures of first order transitions. Fundamentally, what's going on at a first order transition as we go on in this class and we derive the correlation length from the 2-point function, we'll see that the correlation length in a continuous transition diverges to infinity. Well, fundamentally, in a first order transition, it does not. So, again, if you don't know what this means, what a correlation length is, this is what we're going to derive in this class. So instead of thinking of sort of the thermodynamics, in some sense it's what we want to derive. But for the purposes of this class, what we want to think of when we study phase transitions is the lengths, what happens to a length scale, for example. And from this perspective, first order phase transitions are completely boring because they don't have scale invariance, which would come from a correlation length diverging to infinity. And essentially, we're not going to study first order transitions in this class. So I'm not going to say anything else about them besides the fact that on your homework 1, if you came in late, there's some homeworks over there. In question 2, you'll derive the Landau theory corresponding to a first order transition. Okay, it's one Landau theory that can give you a first order transition. So you'll get a chance to look at some of the features of first order transitions in the context of that theory. But basically, what we're interested in this class is continuous transitions. Which I'll call often critical points. For example, that critical endpoint in the phase diagram in the liquid-gas transition. So all critical points are continuous transitions. That's one way of saying, of defining what they are. There is non-analytic behavior at continuous transitions. And there's a correlation length which is fundamental for this class, a correlation length that diverges to infinity. So this is something that we'll explore more. And again, this is the source of scale invariance. And if you take a CFD class, in some sense, that's where conformal invariance comes from too. So as we move ahead, we'll look less at sort of bulk thermodynamic properties and more at this idea of length scales and the RG and so on. But for now, let's just keep moving ahead. So I talked about an order parameter having a discontinuity, an energy, something like that. At critical points, you can have singularities or non-analytic behavior in quantities. For example, a susceptibility for a magnetic system. It's a response function to an applied external field. We'll talk a lot about it. If you measure this in a laboratory, you might see a susceptibility diverging in a certain way. I don't know how it would look, something like this maybe. And that divergence, just like, remember, I defined a critical exponent beta for the order parameter and a continuous transition. This behavior can be characterized, critical exponent. This behavior can be characterized by a critical exponent also, and we'll derive this today in class. And you'll also work on this on your assignment. So T minus Tc to the minus gamma. That's the symbol given to the critical exponent for the susceptibility. And there's two exponents in principle, and we'll talk about that more. One above and one below the transition. Okay. You'll also look at that on your assignment. The specific heat or the heat capacity can also have some sort of non-analytical behavior. I'll call it the specific heat. So near the transition, it can go as T minus Tc to some other critical exponent they call alpha. And you can go on and talk about measuring these in experiment. And what we'll do today is start deriving these in a mean field theory. These are the objects that you expect to be universal. Remember I said beta, I showed this motivation that beta was universal between a liquid gas transition and a ferromagnet. So we'll derive the simplest sort of approximation for these universal numbers. But before I start on that, I just want to point out one thing about phase transitions. and the basically the the thermodynamic ensembles that we calculate them in. So all these microscopic parameters, okay, so all these properties lead to this macroscopic behavior. And we're trying to make this connection between microscopic, say, spins or particle positions and this type of macroscopic behavior. So simply put, all of these curves, I didn't draw a specific heat one, can in principle be deduced from, say, the partition function or maybe the free energy. Various derivatives of the free energy, like the second derivative, might give you a specific heat or something like that. Gibbs says, a thermodynamic definition, say, of the partition function will lead to these types of macroscopic properties that we're interested in. And when I write something like this, I'm writing a trace, if you remember from 704. And what that trace is, if I have a, you can imagine having a finite size system, it's a sum over all degrees of freedom, which is easy to visualize in some cases. And within this sum, I think is what we believe the fundamental complexity of this problem. The inability to somehow take this trace analytically is what leads us to do all of these approximations that we have to do in this class. So this H, okay, so this is a trace. That H is your Hamiltonian, it's classical. Okay, so you're summing over all the degrees of freedom, say, in that classical object, that energy. It's non-singular in the degrees of freedom, and Z is a sum of all those terms. So phase transitions correspond to these big dramatic changes, in some response functions. And there are singularities in the free energy, but how can a finite sum, say, in non-singular quantities, lead to singularities in Z, say? So that some within the calculation of Z lead to non-analytical behavior. And I mean, the more you think about it, the weirder it is. Right? You have this finite sum, and you're asking for non-analytic behavior in this finite sum. How can that arise? Probably most of you know the answer. What is it? That non-analytical behavior, or non-analytic behavior, has to come somehow, in the thermodynamic limit, right? So somehow when if we have a finite size system and we're taking this finite sum, even if that omega is a very large number, that you can't get true sort of non-analytic behavior like this. It is only defined in a thermodynamic limit. So that's just the answer. The answer is, to get this, you need the thermodynamic limit. For those of you that study phase transitions or critical points numerically, all you're seeing is a finite sized remnant of the true behavior. If you're used to calculating susceptibility and seeing a sort of bump there, that's just a finite size remnant. And you might wonder how you can ever study the thermodynamic limit on finite sized systems. And is it even a well-defined question? Are you missing things when you have finite size, even finite size large systems? Are you missing things that might occur in the thermodynamic limit? And so the answer is, essentially, what we'll do in this class is derive scaling forms, essentially from the renormalization group. So the fact that the correlation length diverges gives us finite size scaling functions that we can fit our data to try to give us some clue about what's happening in the thermodynamic limit. So these finite size remnants that we see of this non-analytic behavior still have enough information for us if we know how to treat them carefully. Okay, so generally what this what this class is about is finding this type of behavior in this sort of intractable problem. Okay, and dealing, building a framework, if you will, of approximations that tell us something about what's going on in the thermodynamic limit. Oops. So with that, the idea that there, are macroscopic properties that we're trying to approach, trying to understand. We can only look at, we only have a well-defined, basically a well-defined approach in the thermodynamic limit. Let's look at a specific model called the Ising model, which I've talked about already, that can give us some sort of clue into this behavior and has a nice approximation for this intractable sum. So models, we study a lot of models. Models should do two things. They should somehow be simple enough to solve. I can say that about all models. What's the point of studying a model if you can't solve it, either analytically or numerically? And they should also contain the physics of interest. So the Ising model is simple in some way, and it contains, very rich physics. So the simple model of magnetism that is sort of defined by the Ising model, I'm going to do it like this so I don't screw this up. So I'm going to put a half in front. From a purely condensed matter perspective, you can argue that no magnetic material is simple enough to have a Hamiltonian that can be written like that with only one interaction term. But what we'll learn when we do the RG is many other terms that might occur in real materials, higher order, say, products of spins. So these are Ising spins. Say they can be plus or minus 1 or up and down. So many other interactions are irrelevant from a RG perspective. So we're imagining this is a simple approximation to some interaction that might be going on in, say, a nickel compound. And these I and J points, I'll assume, sit on a hypercubic lattice in d dimensions. Okay, so that's a two-dimensional hypercubic lattice. And the interaction between these different spins, I've just left in a very general form. It's inside the sum, Jij, so that means that any I, in principle, is interacting with any J, everywhere on this lattice. So in a quantum system, I think what I wrote last class was probably SZ. Ising spins are just the diagonal components in the SZ basis. And they can also represent occupation of particles on the lattice. So, an Ising spin up could just be a particle there, a classical particle there. And an Ising spin down could be a particle not there. So the Ising model is very versatile. It's used to model many different things. There's two phases, as I wrote on the chalkboard last class, of an Ising model that correspond to this simple treatment of magnetism. That's the paramagnetic phase and the ferromagnetic phase. And again, phases are defined by the existence or lack thereof of an order parameter, right? So the ferromagnetic phase is defined with a finite magnetization. And what that is, M, is a thermodynamic average of all the spins. I'll write it like this, I guess. Okay, so in your ensemble theory, you would just write that as 1 over Z, trace, say, sigma I, e to the minus beta H, right? So you have a Hamiltonian, very simple. You want to solve for this property. You have this trace that's very difficult to do. The sum over all states, right? And states, if I have a, very large or an infinite size system, right? So you have to sum over all possible, 2 to the n is the size of that Hilbert space, or that state space. So we're not going to do that sum explicitly. We're just going to, actually you are going to solve this model explicitly in question 3. In 1 dimension, okay? So you'll find a way to do this exactly in 1 dimension. And there's a way to do this in 2 dimension due to Onsager too. We won't do Onsager solution in class. So another thing about this Hamiltonian is it's invariant under what I called time reversal last time. Last class I wrote just 2 spins, like a product of, say, sigma I, sigma j. Time reversal is a realization of the Z2 discrete group, remember? Just means if you take a spin, sigma I, and flip it, okay, you performed an operation under this group. You flip it again, it goes back to itself. So that's the identity. So in that Hamiltonian, if you take every sigma and perform this operation, because you have a product of 2 of them, you get 2 minus signs. Minus times minus equals plus. So that's why that is, that Hamiltonian is invariant under this operation. So H just goes back to H. That's the symmetry of the Hamiltonian. That's the symmetry of the paramagnetic state, which occurs at high temperatures. So you should think of a symmetry like this, if it's a property of the Hamiltonian, at very high temperatures, whatever it is, if it's discrete Ising, if it's rotation, at the highest temperatures, your system is invariant in the same way. It's invariant under that operation. And what happens in the ferromagnetic state, which is the low temperature state, is you break that symmetry. And that corresponds with your order parameter turning on. So that's the process of symmetry breaking is what distinguishes basically the paramagnet from the ferromagnet. So all spins up, or all spins down. So if you looked at the order parameter, M versus T, okay, well, you have two possibilities. One is that your magnetization is, say, positive, all spins up, and one is negative. So you can call, say, M naught minus M naught. So whether or not the all up state or the all down state occurs at low temperatures, and you can convince yourself that, that is the lowest energy state. Depends on, it's equally probable that if you cool a ferromagnet down, it'll order in one of the two magnetization states. So that process is called spontaneous symmetry breaking. Below TC here. So if you have a real magnet in the lab, even though those two states are in some sense equally probable, you will not somehow, have both of them at once. You'll spontaneously break the full Z2 symmetry that the paramagnet has. And it's spontaneous because there's no term in the Hamiltonian that dictates that symmetry, that lower symmetry, should be realized, right? You're breaking that full invariance under time reversal. So maybe that's worth writing down. So the equilibrium thermodynamic state, I will say, the paramagnet has the full symmetry of the Hamiltonian. Okay, so let's explore this idea of spontaneous symmetry breaking a little more by adding a magnetic field. So an external field, your model of magnetism. So it's the same Hamiltonian. I'm just going to add a B field to it. So that B affects all spins equally. It's uniform. And this term it's not an additional, there's no interaction between. This is an interaction term. This is an external field. And let's imagine that we're looking at a finite size system. So maybe we have a really powerful computer. We can simulate this Hamiltonian on it. And we're going to take that simulation and increase the number of spins to infinity via some process. And we want to explore whether or not, say, we have spontaneous symmetry breaking in the ground state. Okay, so for very large number of spins, for large N, it makes sense that the magnetization is just, an approximation to the magnetization in a thermodynamic limit is just, if you will, average value of all the spins, right? It's basically the finite size definition of magnetization. I'm just being overly careful with defining things in the thermodynamic limit. So imagine that I'm approaching the ground state in the presence of that magnetic field. Well, that thing obviously, or maybe not obviously, well, maybe if you look at it, it's obvious, it breaks time reversal symmetry. Because in order to be invariant under time reversal, your Hamiltonian can only have a product of spins. So once you put a magnetic field on, you explicitly break time reversal symmetry. So if your magnetic field B, say, is in this direction, whatever this is up on the chalkboard, you fully expect that this will be the ground state and not this, right? If you cool down in the presence of a magnetic field, you'll get one of those two states. So let's imagine cooling down in the presence of that field and then taking that field to 0, say. I'll just say magnetization greater than 0 for T less than Tc. And if it's less than 0, M less than 0. So let me do something here. Let me consider a weird object. Let me consider the relative probability in this finite size system that the magnet, or this model of magnetism, realizes one of these two states. Okay, so I'm defining a relative probability. I'll call it P. And I'll use what we know from 704 to define this relative probability through the, say, Boltzmann distribution. Okay, so near, in the ground state, if I'm in one of these two magnetized states, my first term in my Hamiltonian gives me something like, J, acting on all the bonds, and it's not affected by, again, this process of flipping all the spins. So if I write the Boltzmann probabilities, that'll cancel on top and bottom, and all that I'll be left with C plus and minus B and M. Where I've used the fact that, M is defined there. So this relative probability just gives me something like e to the minus 2b n m, and I'll just write my beta as a temperature. So I'm going to do this probably for the whole class. Set the Boltzmann constant equal to 1. Bn, that's an m. So stare at that for a minute. And think of taking two limits. Think of taking a limit when you have two sort of knobs. One is the magnetic field, B, and one is the temperature. Take one of these knobs as 0 before the other one, and vice versa. What happens to that relative probability? And what does it mean? So I have 3 knobs. I don't want to explore that one. Let me assume we're at T, at low T. 3 is too many. So I have the number of sites in my system. Remember, on a large finite system, I'm taking this to infinity, and I'm taking my field to 0. So I restore full-time reversal in the Hamiltonian. And let's just assume I'm at low temperature. So let me look at these two limits. It's more like an order of limits. So take B goes to 0 from above, say. So I've magnetized myself down here somewhere. And now I'm taking that field to 0. And let's keep n fixed. What happens to that relative probability? B goes to 0, so it's just e to the 0. So then my Pm less than 0 goes to 1. So somehow what this is saying is that the probability of finding the state that I don't expect is going to unity. If you flip this thing around and do the opposite calculation, you find like the opposite thing. And basically, the only solution to this sort of paradox is that the magnetization's also going to 0. There's other ways to think about it, but what this is saying is this magnetized state in the limit where we've restored full time reversal symmetry to the Hamiltonian gives us some problem with how we interpret a relative probability. So the magnetization must go to 0. Let me stay at low temperature and take n to infinity first. And keep B fixed. And say then, afterwards, to restore time reversal symmetry, take B to 0 plus. So then the relative probability M, Pm, n goes to infinity, e to the minus infinity, this goes to 0. Which is what you would expect, right? And the solution to this is that you remain in the magnetized state, right? Which will give you, say, probability 1, and the probability of going to 0, or going to the opposite state in the presence of that field is 0, like it should be. So the system will remain in the m greater than 0 state. And it'll do so even in that limit. The behavior will be non-analytic at 0 field. It'll remain in that state down to 0 field. So I mean, this is just some sort of simple thought experiment. And maybe I didn't explain it all that well, but some variation of this probabilistic interpretation leads inevitably to the conclusion that this type of spontaneous symmetry breaking that we're considering is only a feature, again, of the thermodynamic limit. So we need this order of limits matters, is another way of saying it. Whether we take b to 0 first or n to infinity first, we'll get different solutions. And that's the moral of this story. And as a consequence, because spontaneous symmetry breaking needs this order of limits to be correct, to make sense, it means that well-defined or sharp distinctions between phases themselves are actually only possible in the thermodynamic limit too. So that's twice we've seen this in this class, this idea that we need to worry about taking the thermodynamic limit properly to see the behavior that we expect. So let's be careful when we do that. Okay, so I spoke very generally. I didn't actually tell you what Jij was in this Ising model. Let's do a mean field theory calculation. Who's seen mean field theory before? Okay, almost all of you. I'll go through it pretty quick. Okay, but I think it's also a really important concept, so let's make sure we sort of do it thoroughly. Okay, so in 1D, you're going to do a transfer matrix calculation. In 2D, there's an exact solution to an Ising model, but that we're not going to do, but essentially was done by Onsager. Those give you exact solutions. Now, what mean field theory is an approximation. And you might ask, why are we doing a mean field theory if we have the exact solution? It's because mean field theories are the sort of first order of business for any of these sort of stat mech or condensed matter models that we would look at. Even if, especially in the case when we don't have exact solutions, which is most of the time. Okay, so the exact solution is nice because you can check how accurate your mean field theory is. But the framework of mean field theory is more important than this specific example of mean field theory. So just keep that in mind. So we want to develop a sort of universal mean field theoretical framework. So let's start with asking what we want to calculate. Let's calculate the magnetization, so the order parameter. I think I wrote it like this. And let me write, again, this is basically an impossible problem, generally. I'm just going to say impossible. So let me write this magnetization as one element of okay, so let me write it like this. So let me write the individual variable, sigma I, the spin that occurs on site I, as sigma I minus the magnetization, or the thermodynamic average, So I've just added and subtracted the same thing. This is my favorite way of doing it. Okay, let me substitute this directly into the Hamiltonian and note that the important term in the Hamiltonian is sigma I, sigma j. This interaction term is actually what's difficult to solve. Okay, let me write this out. By pulling out sigma I, sigma j, each minus m. That's this term multiplied by this term. Okay, so then I have basically two of these. And m squared. Okay. One more step. Let me group together terms. Okay, what do I have here? Right, so I have minus 2m squared from these two terms. So let me write those out. So that's, oops. That sign right should be plus sigma j minus m squared. Okay, so this is exact. All I've done is messed around with adding and subtracting, the average magnetization, if you will. So the critical assumption that goes into mean field theory, which is true for every mean field theory, not just the Ising model, is that fluctuations around that mean value are small, or they can be neglected. Okay. So you should think of those sigma i's as being dynamical variables somehow. They have fluctuations. They're maybe existing in a real material at some temperature. But if they don't fluctuate much from the average state, so fluctuations are small, which we haven't justified, but then we can throw away certain terms. So that's a critical assumption that goes into mean field theory. Critical. And this requires some thought. Let's just leave it unjustified. The mean value is m, the magnetization, by definition. And what that fluctuation term is or the largest fluctuation term is this product of differences between the variable and the average magnetization. So let's take this to 0. That's it. That's what defines mean field theory, is taking this term to 0. So however you want to say it, there's many different ways to say it. That's what it is. So with that approximation, the problem becomes infinitely more simple. So let me write out the Hamiltonian now in full. I still have Jij in there. Let me just keep b equal to 0 for now. Okay, so things look different. Now I have a sum over ij and a jij. So this doesn't depend on the position if I assume that the Hamiltonian is translationally invariant. So let me just simplify this with one more step. And I want to call this something. Let me pull out one sum over j and call that sum over jij just equal to ji. I guess I could call it ji, which I'm just going to call j. Assuming translational invariance. You also have to assume that j is probably k local or something like that, or finite. You know, it's nearest neighbor or something like that. So then my Hamiltonian starts looking a lot simpler. Let me pull out the magnetization. There's still a finite size system. Cool. And this is simple enough that we can calculate the free energy from it. And you have to keep in mind, you know, have you thrown out the baby with the bathwater when you make this assumption here? Okay, so we'll explore this a lot more. But for now, let's just calculate the free energy. MJ, yep, that's right. So let's do it like this, minus t log z, where that's the partition function. And the partition function is a trace over all the states. And the only thing you have to know how to do in condensed matter is calculate that trace. So let's do it real carefully. Let me write, as I have been, this e to the h over t. Okay, so what does that trace mean? Okay, you can write that different ways. So you can write it like this. You have all of your sigma variables, and you have to sum over each of their values, plus or minus 1. All the way up to sigma n. And this is written as, okay, different people write this in different ways, I suppose. This trace, you could also write as the sum over the set, I guess, is what this notation means. Or some people might write it as, if you're developing a path integral, this might make more sense as a product. Okay, so So then that partition function, I don't know what's the easiest way to write it. I think the way to do the calculation is like this. Sorry for splitting this up. So let me pull out explicitly the parts that don't depend on the variables. Okay. So you can have an exponential something like that out front. I don't know why I'm doing this, but everything's multiplied here. Sigma 1 equals plus or minus 1 e to the mj over t sigma 1 multiplied by I'm writing too big. E to the mj over t sigma 2 all the way to sigma n plus or minus 1 e to the mj over t sigma n. Okay, when you write it like that, you just see it's a product of a whole bunch of sums. And each sum only has two elements. It's like the local Hilbert space or the local state space, right? So then your partition function, which is just the product of all these, E minus nj m squared over 2t. And let me write it like this. So the first element in the sum is plus. Second sum is minus. E to the minus mj over t. And each, one of these that you're multiplying together is the same. It's raised to the power n. So that's your partition function. This is a hyperbolic cosine. All raised to the n. So your free energy, the thing we want to calculate, has a constant term. Minus something that depends on temperature, log, this thing, 2 cos h j over t. So we have the free energy is a function of the magnetization. Okay. By the principle of least action or whatever it's called. If you minimize the free energy, that tells you what the value of the magnetization is. So we can calculate m from this equation. It's like saying this is the most probable value or the most probable m, So the minimization of the free energy is essentially the basis for what we're developing, which I'll call Landau theory, which is essentially just a non-interacting field theory. So if we set the derivative, partial derivative, say, of f with respect to the magnetization, this gives us our mean field equation. Okay, so that nonlinear equation is what we have to solve in order to get the value of the magnetization for any temperature T. Make sense? So unfortunately, it sucks to solve, even though it's exact. One intuition you'll see for solving this is just plot the left-hand side and the right-hand side separately. Let me call a y-axis and an m-axis. Yeah. And let me say y can be the left-hand side or the right-hand side. So for one of these y's, oh, I missed the origin. That's y equals m. And for the other, it's some function. I don't even know what it looks like. Something like that. And the points where the left-hand side equals the right-hand side are the solutions to the equation. And the shape of, say, the hyperbolic tangent changes with temperature, right? So it either gets stretched out or pushed back. So what happens is you have a solution or an intersection of these two lines for some temperatures, and for some temperatures you have one unique solution, which is zero magnetization. And for low temperatures, you see again, you get two solutions, one for plus, one for minus. If we're near, the transition point, which is where these two curves, where you lose those two solutions, then the magnetization should be small. Right? The magnetization is moving down that curve. So for small magnetization, we can expand out the hyperbolic tangent. I'm only going to use the first term of the expansion right now, but we'll use the second one later. So if you do this, and you plug it into the equation, it gives you the mean field solution for the critical temperature, which is just J in mean field theory. Remember, J is defined way over there. Such a mean field transition temperature. When T is greater than this transition temperature, the only solution is m equals 0. So all those two non-trivial solutions, whatever you want to call them, plus or minus m naught, one is chosen by spontaneous symmetry breaking, right? In the thermodynamic limit. Make sense? This is not the exact solution for the Ising model. Again, it's just the approximation, the approximate solution that's given to us by mean field theory. Okay. you can solve for the magnetization from that equation for all temperatures also. You can do it numerically. And as I've drawn several times, it'll look like this. So let's look near the transition and calculate beta from that, the critical exponent. So to calculate the critical exponent, let me go back to the free energy. And I'll define a free energy, get out of my class. Free energy density is, the free energy expression I have divided by n, okay? And we'll do a Taylor expansion of that. And let's focus near the transition so we can do that Taylor expansion. So free energy density is F over N. I'll probably forget that I call this a density and just call it a Landau free energy. So if you look at your assignment, I'm saying free energy. I'm typically mean free energy density. Okay. Okay, so go back to my free energy expression. And what I need to Taylor expand for small magnetizations, again, because I'm near the critical point. So I'm near the point where this solution's rolling down here. Is this log to Cosh, which I obviously know off the top of my head. So there's a constant out front. Whatever. Okay, so the important thing is the powers of x, obviously. So up to a constant, the free energy density. Let me go up to beta mj to the power 4. Higher order terms and the constant that I'm ignoring. Okay, so just to write this in a different way. I'm going to use the mean field solution for TC here, where it matters. So. Doesn't really matter there that much. And the fourth. So I have a free energy density. That's a function of m, and its functional dependence is m squared and m fourth. And what occurs out front doesn't matter all that much. Although note that this piece here changes sign as you go through the transition. Right? So if you take 733 with me, that's, this is your 5-4 theory, and that's your mass. So your scalar 5-4 theory, and that's what you call the mass of the theory. So the free energy can be plotted for t greater than Tc, which corresponds to that unique solution. And you see that if you plot F. There's one minimum at m equals 0. So that's t greater than Tc. For t less than Tc, you get something that looks like this. Okay, so this has changed sign. So your parabola is upside down, but then your M4 piece keeps it all bounded here. And you have two solutions, minus M naught, whatever that is, and M naught. Okay, so it's a difference between this being positive and this being negative, basically. If you have a magnetic field, which I left out, you just start skewing this. You'll skew these things. That's the most important intuition you essentially need in any of your classes on field theory. Is it's the change in sign of that m squared term that puts you through the transition. Make sense? Okay, so let's keep plugging away to calculate beta. So I have a derivative. Oh, so I have a free energy. If I take the derivative, I can, like I did before, calculate my mean field value for m from this equation. So it'll give me that equation. Let me pull out a power. Is this going to work? Yeah. Okay, I'm just doing this very carefully to get m is two solutions. T over Tc square root okay, so very near the transition temperature, T equals Tc. Then m will just go like Tc minus T. I don't know which way I defined it before, but let's say it's Tc minus T, Tc minus T, to some power, beta, which is your critical exponent, and beta is a half. So again, that's the critical exponent only for this approximation, this mean field theory approximation. I remember I told you experimentally, I didn't tell you the dimension and so on, but beta was some other number, 0.32. So in principle, if you have the Hamiltonian correct and the dimension correct and everything, the difference between the mean field value and the actual exact or experimental value of this critical exponent is due to the fluctuations that you threw out when you define the mean field theory. Okay? So we can do this for other critical exponents. We can calculate gamma. I think that's what you're doing on your assignment. So your question 1 is doing this for the susceptibility. Okay, and so let me just do one case. On your assignment, I want you to do 2 limits t equals 0 and t goes to tc, so t less than tc. So let me calculate the critical exponent gamma for the susceptibility for t greater than, as you approach your critical point from above. Okay. Okay, so the susceptibility is defined as the derivative of the magnetization with respect to a field. Okay, so let's put our field back in. So the mean field Hamiltonian. With a magnetic field will be something like minus B sum over I sigma I. That'll give you a free energy. Okay, so you have basically a magnetization there. So that'll give you a free energy that looks like, and you should confirm this. And it's MJ, here it comes. That's where your B goes. Okay, and then this mean field equation for the magnetization in the presence of a field. Looks like this. So now we can take a derivative with respect to that field, and then essentially set the field to 0 to get the susceptibility, right? Okay, so in your question 1, I didn't put the B field in there, but so susceptibility is a linear response function via that definition. That's why it looks like that. So let's look at the susceptibility in the case where T is approaching Tc from above. I want to do a Taylor expansion of the mean field equation, the hyperbolic tangent equation. I want to be near the transition, so M will be small, but I also have to convince myself that B is small somehow, which makes sense if the magnetization occurs in response to B, right? So M and B are small enough to do the Taylor expansion. It's very simple. We skip all the steps. So that is the thing that I need to take the derivative, partial derivative of with respect to B. All right, so that gives me a susceptibility. Which I'll write like this. Okay, absolute value t minus tc. So here I have a critical exponent, gamma, and it's equal to 1. That's the mean field critical exponent for the susceptibility as you approach the transition from above. Remember on this chalkboard, right at the start of class, I had the two curves for the susceptibility, the two diverging curves for above and below. So in principle, your exponent and also the amplitude, or the coefficient in front here, which I would call C plus for above, and you can have one for below. So those can be different for when, the case when you approach the transition from below. So that's what you'll do in your assignment. Okay, so you'll repeat this calculation for a finite m. Okay, so that's a little tricky, a little more tricky, because you can't assume as you come from below that your magnetization is 0. And then you'll check the exponent and calculate the ratio C plus over C minus. Yep. I want to calculate at least alpha. So I'll do that next time because it's going to take more than 6 minutes. So I'm going to finish up, I'll calculate alpha and I'll calculate delta, the isotherm, the critical isotherm exponent in mean field. And I mean, there's simple numbers like this, 1/2, 1, 0. But what we're doing in this class is basically correcting these numbers. And in order to do that, we have to develop, the next level or the next step of approximation after mean field theory. We got to put back in fluctuations, the things we threw away. And we essentially have to develop the full kind of power of the renormalization group. And then do a perturbative expansion in the dimension away from 4 dimensions, which you'll see why. And that's called epsilon. So we'll be working in a dimension 4 minus epsilon. So we're developing a perturbation theory later in this lecture that it was perturbative into the dimension away from 4, and then we're going to apply it to like 2 dimensions and 3 dimensions. So you might wonder how valid that is, but that's the way, that's the state of the art. And you'll see how these exponents are modified with fluctuations then. And then that's the values that we'll compare to exact calculations on your numerical project. Okay, so that's it. I'll see you guys on Wednesday. This thing's due in 2 weeks, so just bring it to me in class in 2 weeks. And then I'll have another assignment for you. I think you should just be able to go ahead and work on this thing now. Question 2, I call it Landau theory, but all it is this theory where you don't care this microscopic origin of these parameters. I call them phenomenological parameters. So I'll talk more about that on Wednesday. It should give you plenty of time to finish this for 2 weeks. All right, see you guys then.